All right, so we're going to take a look at day 1 of Lab 8. So day 1 of Lab 8 actually had a lot of moving parts, so it's in a way it's kind of nice that we're going to get a chance to do it via video instead of in person. So all of day 1 is considered part A, this procedure part A. And the very first thing you would have done is make some KOH solution. So you would have made it, stored it in a glass bottle, and then used it on day 2 to do a titration. So on day 2, you would have standardized your base, meaning that you would have found the molarity to 4 significant figures. And that's a titration that we do all the time in the stockroom. So before we give you guys a solution, we need to know that the molarity on the outside is correct. And this titration is what we do. But on day 1, we're just making that solution. So procedure number 1, part A and B, is all about making your solutions. So the first thing that you're making right over here is your KOH solution. So you're going to make approximately 0.5 KOH, and you're going to do it by diluting 20 milliliters of 6 molar KOH. So in other words, the solution that I would have out for you is the 6 molar KOH, and you're going to take 20 milliliters of it, and you are your goal is to make a 5 molar solution. So you're going to use M1V1 equals M2V2, and you're going to be solving for V2. So you're going to find out the total volume of solution. So the 0.5 molar KOH, that is your M2, that's the molarity that you're going to make. The 20 milliliters is V1, that is the amount of your original solution you're going to use. And the M1 is the 6 molar KOH, that's the bottle that would have been in the lab. Now when you solve for V2, you're going to be finding total solution. However, I need you to not only find total solution, I need you to find the total milliliters of water needed, because if this was you in the lab, you would put in 20 milliliters of KOH and you would put some amount of water. So you need to know how much water would go in to make that final volume of solution. So let's just take a look at this. So M1V1 equals M2V2. So the starting molarity, again, that was your 6 molar KOH that you would have found in the lab. V1, that is the amount that you would have added, which is 20 milliliters. M2 is the new molarity, and we've asked you to make a 0.5 molar solution, and V2 is the new volume. That is what you're going to calculate. So you're going to find this. But as I mentioned, if you're really going to make this in the lab, you're going to take the 20 milliliters of our solution and some amount of water and mix them together. So what you're going to do is take V2, which is your total volume, and then you need to subtract out the amount that you initially added. So you're going to take your V2 and you're going to subtract out V1. V1 was the amount that you added of the 6 molar KOH, and this will give you your volume of water. So let me write this one other way, and that is you're going to take your total volume, which was your V2, and you're going to subtract out the volume of KOH, and that will leave you with the volume of water. Because you only have 2 components, KOH and water, so if you know your total volume and you know how much KOH was added, you can then subtract to find the volume of water. Now, if this was a regular semester, I would make you show me your final volume of solution and your milliliters of water before you started, just so you didn't make a mistake when you were making your KOH solution. All right, so next up is part B. In part B, you're going to make that 0.5 molar HCl. So what you're going to do is dilute 5 milliliters of 6 molar HCl. So we would have a 6 molar bottle out for you. You would take 5 milliliters from there, and you would need to add enough water to get a 0.5 molar solution. So you would do it the same way with this M1V1 equals M2V2. And just like you did down here, you would solve for your V2 and then find your amount of water by taking V2, which is your total volume, subtracting out V1, which is your KOH, to find the volume of water. So for both A and B, I want you to find V2, which is the volume of solution, but then subtract subtract using V2 and then V2 minus V1, V2 minus V1 to get your milliliters of water added. So these are two of the three solutions you would have made. Now part C is making an NaCl solution. So for your NaCl solution, you would have put a little bit of NaCl, which is table salt, right into the bottom, just the curved portion of your test tube, and filled the rest up with water. And by the rest, I mean really about halfway. Stirred it up with your glass stir rod, and then that would be your third solution. So you can skip this part, because we obviously can't have you make that unless you wanted to make it at home with some table salt and, I don't know, a very small glass. I was just teasing. You don't need to make a NaCl solution at home. All right. So next up, you would have done a litmus paper test with all three of these solutions. So we would have had you pour a little bit of your KOH into a test tube, a little bit of your HCl into a test tube, and a little bit of that sodium chloride into a new test tube. So then you have three test tubes with about the same amount of solution in each one. Here we say about 2 milliliters of each. And then what we would have you do is a litmus paper test. So before we go on, I want to show you a short video on how to do a litmus paper test. Oops. Here it is. All right, so here's a litmus paper test. All right, that was a very quick litmus paper test, so let me go over what they did. Now, they actually used kind of a bad procedure, in our opinion, and that is, first of all, they used the entire piece of litmus paper, which is kind of wasteful, but also they dipped it into their solution, and that is a bad idea because that litmus paper is soaked in dye, and once you put it into your solution, that dye can bleed out into your solution. So instead, what we ask you to do is use a watch glass. I know my artwork is not wonderful, but this is a watch glass. Next time you are in a lab and you want to know what your watch glass is, to me it looks like a giant contact lens. Sorry, that's my frame of reference. All right, so here is the watch glass from the side, and here's a top view still of the watch glass. And what we've done in our lab is we have cut up your litmus paper so they're in small pieces. We just find people aren't as wasteful with small pieces as they are with the large ones. You saw the people in the video being quite wasteful. All right, so we have two different types of litmus paper. Those of you going on to Chem 1B, you're going to find that there's even more litmus paper there, but this is for a simple acid or base test. So the blue paper, the blue litmus paper, will turn red in the presence of an acid, and the red litmus paper will turn blue in the presence of a base. So again, this litmus paper is only good for determining if you have an acid or a base. But let me talk to you a little bit about the technique. And I know this isn't as much fun as seeing a live demo in class or playing with it yourself, but I'm hoping that this helps. So here is my glass stirring rod. In class, you would have found that in a box right near the window. And of course, you would have cleaned it off, dried it, and put it back. And over here, you have your test tube, and I probably have way more solution than you should have had in that one. You just need a tiny bit in the bottom. Okay. So now what I would have you do is take your glass stir rod, dip it in, and you don't need to go all the way to the bottom. This should have already been stirred with your glass stirring rod, so at one point you stirred this up. Now when you're ready for your test, all you need to do is touch the top, and then you're going to come over here and just touch your litmus paper briefly. Now, even though we've cut up the litmus paper, you can still use it for 2 or 3 tests. So let me zoom in here. And here's a blue litmus paper, and I have a red spot on it. So that red spot is the liquid that came from my solution. So the blue litmus paper will turn red if your solution was acidic. If it is not acidic, it will not change color. So if it's either neutral or basic, we won't see a change in colors. And what a lot of people will say is, hey, my litmus paper is just getting wet, it's not changing colors. Well, that wetness is just it showing that it's not changing color. So if it just looks wet, that means your solution is not acidic. It's either neutral or basic. All right, so down here I have a red piece of litmus paper with a blue dot. So if you were testing a base, you would use your red litmus paper and you would place that glass stir rod, just barely touch it, and you would get a blue dot there if it was basic. If it was not basic, if it was acidic or neutral, again, it would not change the color and it would just appear wet to you. All right. So that's how we would do a litmus paper test. So now let's talk about what you're going to do for your lab here. Oops, right over here. Okay, so here are your solutions, NaCl, KOH, and HCl. And what you would be doing is testing them both with blue litmus and with red litmus paper. So let's talk about that blue litmus paper. So what we said about the blue is that it will turn red if it has an acid. All right, so the only acid that we have is HCl. So the only one of these three chemicals that can turn the blue litmus paper red is going to be HCl. So I'm going to ask you to go ahead and pretend this is a live lab. Use a pen here. This is lab data. So the HCl would turn blue litmus paper red. Now for the other two, you're not going to see any change unless you want to notate that it looks wet. But I'm going to go ahead and say no change. You could also say blue, or you could say wet here. Because it just looks blue, it looks wet. So I'll just go ahead and say no change though, because we don't see any change in the color. But again, if you want to say blue or wet, that's perfectly fine. All right, so next up is the red. So for our red, it will turn blue in the presence of a base. Well, we only have one base here, and that is our KOH. So the red litmus will turn blue only for the KOH. NaCl table salt is neutral, so you would see no change. And HCl is acidic, so we would see no change for a red litmus paper. Okay, so I'm hoping that that makes sense here for the litmus test. Those of you who are like, oh, I'd like to see more of what a litmus paper test looks like, you can find them all over the internet, and if you have any questions about it, I'm happy to talk with you more about it. Next up is the flame test, and flame tests are super cool, so I'm going to go ahead and start off with what I think is a pretty awesome video. All right, this is the Megalab flame test.
This is our flame test for our Megalab. The substance that I am testing in this video is lithium. So we're going to observe what color. This is lithium. Remember that you want to be descriptive with your colors. Calling this red may not be a good description. You may want to say something about the pink tones that are in there, because there may be another substance that we test later that also will appear to be a red color. So we want to just be extra descriptive with our colors. This substance is going to be sodium. I need to clean my wire real quick and heat it up so it's ready to test. And then you can see that sodium burns kind of like a bright yellow with a strong intensity to that flame. And that is sodium. This is going to be the test for potassium. See that potassium is a lavender type color. This substance is calcium. Calcium burns a bright red orange. You saw it there at first. Did a little bit more. See that bright red orange? Different than the sodium was more yellow, where this is more orange. This is strontium. Strontium and calcium seem to be pretty close in color. And this one I think gives off a little bit more red, perhaps. More of a pinkish red. See if we can get a little bit more, just to see. This is a red-orange. So you may want to go back and look at the calcium one and compare that to the strontium one. This is barium. It appears to give off a yellow-green color. Now it's gone. So as soon as you touch your substance into the flame, that's the color that you're observing. The longer you hold it in there, the longer the chance of having it burn off is. So it's that initial color that you first witness when you put your substance into the flame. Is what you should be observing. You can see it gives a yellow-green color. And it's gone. Our last substance is copper. And you can see this puts off a bright blue-green color. Different than the barium. The barium was more yellow-green, whereas this is that bright blue right in the center and green highlights on the outside. I'm not really sure what the yellow is jetting off of that, but that typically does not happen. So you should be looking at that blue and green is copper.
All right, so that is a flame test, and flame tests are really cool. What you're looking at in a flame test are the metals. So we're looking at these metals right here. Oops. These metals right here. And what's actually going on is described in this PowerPoint, so we're not quite there yet in lecture, but we will get there. So here an electron can absorb energy and jump from its ground state. This is where it normally is. Those of you who know about electron configurations from Intro to Chem, this is from its standard electron configuration, where it's supposed to be, where we would assign it an orbital, to some higher level. So they can jump up, and we call that excitation, and then afterwards they will relax back down. So they absorb some kind of energy. It could be heat energy, energy from that Bunsen burner, it could be electricity if you're plugging them into a light socket, but something gives them enough energy to jump up to a higher state, but eventually they, again, do have to come back down. They don't always come back down immediately to their home. Sometimes they come down in steps, and that's what you see here. An electron jumped from the first energy level to the third, and now it relaxes from the third down to the second. But something very interesting happens when it relaxes. It has to give back that energy, and it gives it back in the form of light. So when we see these colors, what we're seeing is a light emission that's happening as it relaxes. So essentially you're seeing it give back that energy. And this is something everybody has seen before. If you've ever seen a fireworks, all those colors in the fireworks, those are all depending on how far down this element relaxes. So if it relaxes for quite a long distance, so if it essentially makes a long fall, that's a high energy fall, we're going to see a high energy color, something more like lavender or purple. Whereas if it is a short fall, like you see right here, it's just a one energy level fall, you're going to see a low energy color, something like red. So again, that's exactly what you're seeing in your fireworks, and we'll talk more about those in a later chapter. But let's go ahead back to our flame test. So what you would have done in your flame test is a little different than what they did in the video. So in the video they used a nichrome wire, and nichrome wires are great because they don't melt and they don't react with the flame. So they dipped their nichrome wire in solids and then stuck it into the flame. What you would have done is use splints, and those are basically popsicle sticks that we have broken in half to conserve. And then I soak them in distilled water for you. And the purpose of that is that we don't want the stick to essentially absorb all of the compound so we don't see any color. We want the water to saturate that wood so that when you dip it into the solution, that solution is on the outside and the flame has good access to it. All right, so you would have taken 1 splint for each one of your test tubes. And just to remind you about your test tubes, you have potassium hydroxide, hydrochloric acid, and NaCl. All right, so each one of them, you would have placed them into the flame. Now here's an image of your Bunsen burner. And I hope you have seen in class that there is an inner cone, which is blue, and then you have the outer cone, which is hopefully also blue, but it's that inner cone that is the hottest, and of the inner cone, it's the tip that is the hottest part of this whole flame. So what I would have had you do is take your splint and put it directly into the flame right at that tip of the inner cone. So one of the problems we sometimes have is if you dip this in your solution and then you come down, it actually burns it off up here before you really get a chance to see the color. And that's why I always recommend you go right in horizontally, directly to that tip of the inner cone. All right, so now let's take a look at your lab data. So again, I want you to write this in pen just as if we were doing a real lab. It is a real lab, it's just online. All right, so starting with our NaCl. So let's go back to our video and take a look at that NaCl.
This substance is going to be sodium. I need to clean my wire real quick and heat it up.
There it is. All right, so here's our NaCl. So sodium burns with that yellow-orange flame that you would see if you had a campfire, or really most fires, we see that yellow-orange flame. And the reason it is that color is because of sodium. Sodium is everywhere. So if there's nothing else to change the color of the flame, we usually see the color of sodium. And as you saw in that video, they had a little bit of a hard time cleaning off the sodium, and that's perfectly normal because, again, sodium just tends to stick to everything. So for your sodium, you're going to write what you see here. So if you see colors differently, I would like you to write it the way you see it. The idea is that these are a fingerprint so that whenever you see this color, then you will know that it's sodium. So if this does not look yellow-orange to you, if you see a different color, please write down, again, whatever color it is that you see. All right, so we've just talked about what you're going to write here, which is sort of a yellow-orange or whatever color you're seeing. Next, let's go to our KOH, and what we're really looking at is the potassium. And I'm just zooming along here trying to find our potassium.
I want to go back and look at the calcium one and compare that to the strontium one. This is barium.
The sound is off for me, so it's a little harder.
Appears to give
Oh,
off
that is not
a
potassium.
yellow-green color. And now it's gone. So as soon as you touch your substance into the flame, that's...
And again, the sound is off for me, so it's a little harder
So you
to
may
see
want to go
if
back and...
That is indeed our potassium. Doesn't quite look like it. I'm trying to find the purple lilac color.
And then you can see that sodium burns kind of...
That is our sodium.
This is going to be the test for potassium.
There it is. All right. So these have a very characteristic color, and that's how, even without the sound, I'm able to kind of fast forward through here. So it is sort of a purple or lilac color. You're seeing a little bit of the yellow through there, and that is the yellow of sodium. Again, it's really hard to get rid of that sodium. So a lot of times when we're looking at potassium, we actually look through something called a cobalt glass, and it is a piece of glass that blocks out sodium and other elements that might be getting in our way. So it's really hard to see, but there should be something purple-ish, so purple, lilac, lavender, something like that should be what you're seeing here. But again, if you have a color difference, please write whatever color it is that you're seeing. We're not looking at there's sort of a yellowish white in the background. We're not looking at that color. We're looking at, on my screen, I kind of see it a little bit on the left side and then sort of dancing in the flames. To me, it looks like a purple-ish color. So whatever color you do see there, that's what you're going to write for your KOH. So next up is HCl. And now HCl does not have a metal that's going to show its own color. Because there is none, we just see what is essentially the background, and that is basically the background that we see anytime we don't have a metal showing its own color. So this should be the same as NaCl. Which is to say that because there's no other color overwhelming the sodium color, you just see the sodium color. Now I've marked it as the same as sodium chloride, but that's not what you're going to put. You are actually going to put the color that you saw for sodium chloride. So whatever color it is you saw up here for sodium chloride, some kind of like an orangish, yellowish, whatever you saw, write that same color down here. And again, make sure you're writing it in pen. So I'm sorry I didn't get a chance to show you all those flame tests in person. They are very cool, but it was a pretty cool video too. All right, so next up is the indicator test. So we'll use phenolphthalein as our indicator, and we're going to test each of your three solutions, NaCl, KOH, and HCl. But before we do that, let's take a look at another video.
In a slightly basic to the first pH indicator I want to show you is called phenolphthalein. Phenolphthalein is probably one of the more common pH indicators we use because at pH 8 or lower, it's colorless, and at pH 10 or higher, it's a deep pink. So an acidic solution is going to be colorless, and in a slightly basic to strongly basic solution, it's going to be pink. This makes a very good indicator for a strong acid, strong base titration, or a weak acid, strong base titration. What I'd like to demonstrate to you is how this would work in a titration. This currently is an acidic solution. It is colorless. I'm going to add dropwise a base solution to show you how a titration may occur. Adding a base, you'll see right away the very vibrant pink, but when I swirl it, the pink does go away. As the pink starts to stay around for longer periods of time, we're getting closer and closer to the equivalence point for this pH indicator. Just a few more drops, I believe. Every once in a while, it's good practice to wash down the outsides of the Erlenmeyer flask with some DI water to make sure all the base gets in there. You see that pink color staying just a little bit longer each time I add a drop of base. Until right now, it is a very, very pale pink that disappeared. The next partial drop is probably going to be my equivalence point. Wash that down. Oh, still another partial. Titrations require patience.
All right. Okay. So phenolphthalein is an indicator that turns pink in basic solution, but it is colorless in neutral or acidic solution. So the reason we use it for titrations is it helps us determine where our endpoint is. So we stop titrating, we stop adding base when it becomes pink, and you saw a little example of something that's close to a titration. It's not actually a titration because they didn't use a burette, but it's similar to one where they added the base through their through their eyedropper. Okay, so only one of these three is a base, and that is our KOH. So it is only the KOH that should be pink. The other two should be colorless. Because again, only base will turn it pink, and there is a note down at the bottom that says that the appropriate description is not clear. So when you see a solution that appears quote unquote clear, we would like you to use the word colorless. So colorless denotes that you don't see any color in there. Okay. So next up, you're going to write the formula of your neutralization reaction. So for your neutralization reaction, you are reacting HCl and KOH. So that's your acid and base. It's a double replacement reaction. So I want you to write it out here. You don't need to include the steps, but please do write that out, and you can write it in pen or pencil. All right, so next up, we would have done something similar to a titration, and it's actually the same thing they showed you in the video. So in the video, they had a Erlenmeyer flask that had their acid, and then they would drop in slowly the base until it turned pink. Well, you would have done the same thing, except you would have used litmus paper. All right, so you would have gotten to choose your litmus paper, red or blue. This time, unfortunately, I had to choose for you. I'm going to choose red. Those of you who are like, no way, I'm a blue person, I'm not a red person, I'm going to choose blue. Feel free, but be aware that if you choose blue, the answers below would change. All right, so I'm going to go ahead and choose red. And now we're asked for the color of the litmus paper with HCl. So what we know about our red litmus paper is it turns blue in basic solution. However, it will only turn blue for basic. If it is not basic, it is going to stay the same. So that is to say the color of the litmus paper with acid should still be red. It shouldn't change colors. Next up, it says color of the litmus paper with HCl after neutralization with KOH. So you've added enough KOH so that now we're seeing a color change. So KOH is a base, and what we know is the red turns blue in basic. So now you should have blue litmus paper, or at least a blue dot on your litmus paper. So again, if we start off with red, the color of the litmus paper with acid in it, it's still red because it can't change unless it is a basic solution. But now we've added our base in the second part over here. So you added your base, now you have a basic solution and it turns blue for you. So make sure you fill in the words there, and this is part of your lab data, so make sure you're writing in pen. Below it says number of drops of KOH required to neutralize the HCl. Well, you didn't actually do it, so go ahead and skip that because you don't know how many drops. All right, so the last part of day one is part G here, and it says transfer the test tube to boiling water bath, and you're going to heat the mixture until it's been vaporized. So you would use something that we call it an evaporation dish. It is a porcelain container, sort of like a crucible, but it's more in the shape of the watch glass. So it's really good for heating things and driving off the moisture, getting any kind of water to evaporate. So we want to do this slow so we don't get any splatter. And when we want to heat things very slowly, we like to put them on a boiling water bath. So what we've done is we have a hot plate down at the bottom. And here's your hot plate. And then on top of the hot plate, we have a beaker. And I know it looks nothing like a beaker, but trust me, it's a beaker. All right, so this is your beaker right here. That looks nothing like a beaker, but it is. And it is boiling water. So we put the evaporating dish on the top. So the evaporating dish is actually getting heated by the steam. So it's sort of like if you have a steamer. So when I bought my set of pans, there's a pan that you could fill with water and then another pan that actually fits in the top. It sits on the top, and the way it works is the bottom pan, we heat the water and the steam rises up and there's holes in the top pan. So if I put spinach or something like that in there, that spinach is being cooked by the steam. That's the same thing that's happening here. And the difference here is that we are driving off all the water. So all the water in your solution has been driven off. Sorry, I'm overkilling on the on the highlights there. Okay, so you're driving off all the water. So what is going to be left is any solids you have. And here's that equation that I wanted you to do. Pretend you haven't seen it when you write out your equation. HCl and KOH come together to make KCl and H2O. However, once you put in your evaporating dish, it's got a little spout here. All right, once you put all this in and then you heat it, remember it's on top of a beaker. That's on top of a hot plate. I have to label my drawings because they're so bad. We have driven off all the water. So after the experiment, the only thing you have left here is the solid. And that solid is your KCl. All of the water is floating around up here as a gas. So it is floating away, it's gone, it's up the fume hood, out the building. And what you've got left again is that KCl solid. All right. So the next part asks you to test that solid. So first off, solid observed after vaporizing the liquid, and I'm going to say yes, you would have the solid, and again, that'll be your KCl solid. Then you're going to use the flame test. So same kind of flame test that you did before, but you're going to use it to identify that potassium there. So what you would write right here is the color of that potassium. So the color of the potassium you already know from way back when. And here it is right over here. So that potassium, remember that was a purple or lilac or lavender color. Whatever color did you think you saw there, that is the same color you would get from this flame test. So I know sometimes the question's asked, well, hey, why do we do flame tests? This seems kind of unneeded. And the flame tests are really good for identifying which metal you have. So next semester, those of you going on to Chem 1B, you're going to get to qualitative analysis, where you're going to try to identify what your ions are. And one way to identify a cation, a positive ion, a metal ion, is to put it in the flame and see what color it turns. So if you were to do that, and if it were to turn that purple lavender color, you'd be, I know what my cation is. It's potassium. Or you could say maybe it turns that green, that deep green, sorry. Maybe it turns that kind of deep green you saw at the end of the video. And then you would say, I have copper. So it is used as a fingerprint to identify certain metals. And very cool, next time you're watching the fireworks and you see those fireworks go up, you can identify which metal you're looking at by its color. So what you could do is study up before you go to the fireworks next time, and even bring a little cheat sheet of what color goes to which metal. And as your family and your friends are like oohing and awing, you could be like, oh, excuse me, did you know we're looking at strontium right now? And they will be so impressed. All right, so that is the end of the procedure part A. That is the end of Lab 8 Day 1. And there is also a video online for Lab 8 Day 2. All right. So